Hello, everyone. Thank you all for coming. It's nearly a full room. Like he said, I work at Zcash, and I won't go into it too far, but Zcash is basically Bitcoin, but with privacy. Because if anyone has told you that Bitcoin is anonymous, that person has lied to you. But we actually do have privacy, and we deploy a bunch of really interesting, sometimes novel cryptography to make that happen. But we write it mostly in Rust and C++. So when I recently had an excuse to go back and write something in Go for a change, I got a little bit carried away with it. And I wanted to write not just the code in Go, but also the code in Go that is equivalently fast to its Rust and C++ equivalents. And this is a talk about how I got there. So first we'll back up and explain a little bit what this code actually is. This code is a hash function called BlakeTo. A hash function is a type of function generally that takes a variable length input and produces a fixed width output. There are additional properties that it might or might have, but that's the core thing. If you've heard of SHA-2, that's a hash function. BlakeTo is a newer hash function, and BlakeTo is awesome. That's a speed chart on the right, and it might be a little hard to read, but just notice that BlakeTo is at the top. So it's very fast, but it's also immune to some attacks that affect MD5, SHA-2, that kind of thing. And it's got all of these features, like it supports parallelism natively, it does a thing called tree hashing. There's all this stuff. But the problem is, no one actually implements all of those features. Most people only implement BlakeTo kind of in a mode that makes it exactly analogous to SHA-2. But because, as I mentioned, we're doing a lot of exotic cryptography stuff, we actually want those features. We want to implement those features. We want to use them for things. But since we don't have a specification, we're implementing in kind of an unknown gray area. And if you've ever heard people talk about implementing cryptography before, you probably know that when you're implementing cryptography that doesn't have a spec, you're playing an extremely dangerous game. Incidentally, this photo is believed to depict two TLS 1.0 implementers doing interoperability testing. So we want to implement BlakeTo anyway, and we're kind of in a gray area. So that means that what we want to do is implement it more than once. We want to implement it independently a couple of times. And we already had one in Rust, so this is my excuse to do one in Go. We want to implement it independently, take the output from those independent implementations, produce a set of what are called test vectors, and make sure that all of the implementations agree on what the output should be. So what does BlakeTo do? Well, you initialize some parameters, you split your input data into blocks, then you scramble the bits around somehow, you update an internal hash state, and then you finalize that state to produce an output. If you've looked at hashes in Go before, you've seen the hash interface. You have an embedded I/O writer. You have a sum function that produces that final output. You have a reset that brings you back to the beginning as if you'd just initialized a fresh hash. You have size, which tells you how big the output will be. And then you have block size, which tells you something about how much input the hash will take before it needs to update its state. This interface doesn't work for BlakeTo. But that's another talk entirely. This one's about benchmarking. So in order to do benchmarking, we're going to use a couple of tools. Go has a really good benchmarking ecosystem. First, there's GoBench, which is built into the Go tool. Dave Cheney wrote a great blog post about it here. There's BenchStat, which will take a lot of output from GoBench and do some statistics on it to tell you how faster or slower it is and how reliable those numbers are. And then there's pprof, which is our profiler, which tells us in much more granular detail what our programs were doing during the time that the benchmark was running. There's also this awful bash one-liner that I use to string all of these things together. If you start doing this, you'll come up with your own. Moving on. Go has built-in support for benchmarking. It's testing.b, not testing.t. I do put my benchmarks in test files. You don't have to, but I think people usually do. And you can, if you can read quickly, you can follow along with my benchmarks here. But what they look like is this. I have this function, benchmark hash size, that takes a parameter for how much data we want to write in a given benchmark. It sets some benchmarking settings, initializes a new digest, writes the data, and then produces an output. And you can see at the bottom there that a specific instance of this type of benchmark is only hashing 8 bytes. The magic here is that b.in value that comes from testing.b. The benchmarking suite is going to scale that automatically when we run benchmarks until the function runs long enough that it can make reliable measurements. So if your function is very fast, b.in is going to be very high. And if your function is slow, b.in will be low. So if we run these benchmarks, and I've got the 8 bytes one that hashes a kilobyte, and one that hashes 8 kilobytes, we will see that the numbers we're getting from an RFC spec implementation of Blake 2 are nowhere near the almost gigabyte a second of throughput we would expect from the speed chart earlier. We'll also note that for later that we're running about a 6-second benchmark. So what is slowing us down? Obviously, it's something. This is where pprof comes in. If we run pprof on this code, we'll see that it has a feature called top 5, which gives us our 5 hottest functions. Compress and g, whatever they are. Math bits, which is going to be some kind of bit shifting thing. Allocations and slices. But we don't yet know what the relationship between these things is. pprof, though, has a whole bunch of other features that will do this for us. So if you'll bear with me for a second, I am going to try to show you probably my favorite feature of pprof. It's called the WebView. And so we're going to tell pprof that we want the WebView of everything, that just the any character regex here. Incidentally, this is Brave on a Chromebook. Yes, use Brave. OK, great. So we've got this call graph that it outputs in SVG, and it tells us the order of calls starting from the benchmark launch all the way down into our code, annotated with the profiling information. And so we can see here that we've got those top 3 functions that we were talking about, right? We've got compress, which calls into g, which then calls into the math bits stuff. So we know now that instead of being 3 independently expensive things, these are actually part of one hot loop where compress calls g, calls math bits. So we're not actually going to fix math bits. That's in the standard library. That's a little bit beyond the boundary of things we can reasonably manipulate. But G and compress are both our code, so we can do whatever we want with them. And we'll want to start as far down in that call graph as we can. So we'll start with G. And if you remember in the algorithm, G is the part that scrambles the bits around. And implemented a little naively, it looks like this. It takes a whole bunch of integer parameters, it adds them together, it shifts them around, and then it returns those manipulated values. And you can see here also the bits calls that were showing up in our profile as well. Now, because it takes integer input and gives integer output and doesn't have any side effects and is a very small function, This makes it a really good candidate for an optimization called inlining. Inlining is when you copy the body of a function into the body of the calling function. And you do this because it avoids function call overhead, which in Go is pretty substantial. But obviously, if you are copying functions into everything that ever calls them, you're going to end up with a much larger binary size because you'll have a lot of redundant code. So in order to manage that trade-off, the Go compiler has a component called the Inliner, which applies some heuristics to take care of this for us. Specifically, what the Inliner does is visits the compiler's internal representation of the function during build, and applies some heuristics to calculate a complexity score for that function. It'll take that complexity score and then compare it to some maximum budget, which is always fixed. It's a property of the compiler and not anything that we can control. And it'll see if the compiler, or it'll see if it thinks that the function is too complex to be inlined or not. And again, this is a trade-off of complexity, binary size, and a couple of other things that we'll see in a sec. But what this means is that there's a part of the compiler that determines whether or not this G code is going to be fast, and we don't actually have direct control over it. So we're going to have to figure out how to make the compiler happy with our code. But there's a set of rules for this. The inlining heuristic is really well explained in the compiler code, although I think it's not documented anywhere else. But what it does is visits all of the instructions. Each instruction is +1 cost. Slices are pretty expensive, so the heuristic adds +2 or +3 to any instruction node that deals with slices, and then function calls themselves cost +2. Although you can sometimes further inline if that target function is inlineable and small. But the call will always cost +2 regardless. So this gives us a rule set for how to write our small math functions in such a way that the compiler will inline them. Though there are a couple of hard stops, like I said, the function has to be simple. It can't have any kind of nonlinear control flow. It can't recover, but it can panic. That's very new. And then there are certain runtime functions that make assumptions about like the runtime state. And if we inline, we'll end up breaking them. So if it sees those calls, it will also not inline the function. As I said, the full details are in a file called inl.go in the compiler source tree. But this does give us a set of things. We know what will make stuff more expensive, and we know what we can and can't do. We also, well, I'm going to go ahead and skip ahead here. This sounds like a pain in the ass, but it is worth doing. In this particular case, making the round function g inline is worth almost a 70% throughput improvement in our hot loop here. And it propagates down to the smaller benchmarks as well. So this is well worth doing. But we need a set of tools to figure out how to make it happen, right? You can't just like stare at the code and decide if it's going to inline. You need the inliner to tell you what it thinks of your function. You can do that specifically with some GC flags arguments in your tests and in your builds. -m2 will put you into a sufficient debug mode. And you can see here that our function g won't inline because it costs 133 and our max budget is 80. OK, so g is too expensive. What is g doing that the inliner is not going to like? Well, the first thing here is all of these bits calls, right? And regardless of what rotate left 32 is doing, the inliner is still looking at those function calls and saying, oh, I hate function calls, +2 for each of those. So the obvious first thing that we can do here is get rid of those function calls. If we replace our lovely, convenient standard library calls, yeah. If we replace our lovely, convenient, readable standard library calls with their exact equivalent bitwise operations, we will find that we are now down to 81. Yeah, 81. Almost. So close. And all it came was at a cost of, some readability. It's fine, right? But we're down to 81. So we need to look at this and think, all right, one more point. We have our inliner rules. We are 1 point over the line. What else can we do here? And I will wait a second while you think about it, because it's a tricky one. That's a reasonable answer. Anyone else have a thought? All right, so the answer here, which people yelled at me at when I explained about, is actually cheat. We're going to change the API, because this is a code in our own internal loop. It's not externally facing. We can change whatever we want about it. So what we're going to change here is this first triple addition. Because there are no data dependencies between this value of a and anything else in the function, we can actually just say, OK, when you call us, make the value of a already be that. And this is great, because now the inliner loves us. We now cost 74. And we'll be fully inlined, and we'll get that 70% performance bump that we were looking for. But that doesn't mean that you should attempt to write the lowest AST budget code you possibly can. In fact, please don't do that. Under budget doesn't mean faster. The inliner is a heuristic. It's not directly measuring performance. And the gain that you'll get from bypassing function call overhead is both pretty situational and a threshold effect. You're either being inlined or you're not. You're making a function call or you're not. So if I made this function be 50 points, it wouldn't be any faster than it is at 74. Definitely don't chase this. You'll know if you need to do it, you can, but otherwise, please don't. So what's next? We've got our G function inlining. Our code is much faster now, but when we run pprof, we'll see that the ordering of our hot functions is actually still the same. It's still compress, G, malloc, some other memory stuff. We don't really know, although you can see that pprof is smart enough to tell that G is being inlined now. It's a great tool. But we don't really know what is happening in compress that's taking up all of this time. We need a more granular view. So we're going to go back to pprof and see if it has any more advice for us. Spoiler, it does. Cool. So pprof. The tool that we want here is, and I apologize, I'm going to have to check which Git branch I'm on. Yeah, cool. Is actually called web list. And it's going to take the same kind of parameters. It's going to open the browser again. And it's going to give us, instead of that graph view, a list view. This is a line-by-line profiling data for everything that pprof has seen our function do. So you can see all these internal runtime stuff. But what we're interested in is compress. So we're down here at compress, and we can scroll through and look at our profiling data. And we can see that this cumulatively took longer than this. There's 10 milliseconds for a copy, that kind of thing. But then we see these two lines. These two slice lookups here that collectively occupy about 1.5 seconds of our total 6-second runtime. So it's pretty intuitive to think that those might be the problem here. But again, as with opening WebList in the first place, we still don't know what about this is slow. We want an even more granular view if we can get it. And pprof will give that to us. If we just click on this line, it'll do a full disassembly and tell us what exact machine instructions are being executed to produce that line of Go code. I won't expect you to learn or understand assembly here. Hang on, let me close this. Now that you know how to get to this, I will show you a helpfully labeled version. We're doing this triply indirect lookup here, and you can see that there are some CMP instructions, which is a comparison of some sort. Then JAE is a type of jump, and we're doing that a couple times. But what those are doing is jumping to a call to runtime.panickindex. So what this code is doing, what these instructions specifically are doing, is comparing our array or our slice access to the length of that slice as the compiler knows it, or at runtime. And then if we're out of bounds, it's jumping to a panic function. And you've seen panic index if you've ever seen this error in your code. This is what's happening when you request an out of bounds index. So what we're seeing here is bounds checking. This is a thing that the Go compiler and runtime do to keep us safe from ourselves. Out of bounds memory accesses are a cause of vast numbers of security vulnerabilities in C code, but Go prevents them, and this is the mechanism. This is how Go stops us from doing that, by looking at our array accesses and deciding whether or not it should insert these safety instructions. So safety's great and all, but we're trying to go fast. So we would really like it if we didn't have to spend time doing these comparisons. We would like to eliminate the bounds checks. There's a much easier way, actually, to see if there are bounds checks happening. As of Go 1.7, there is something in the compiler called the SSA, the single static assignment representation. We won't go into what that means, but what it means for us here is that we have some fancy new debug output, and you can see the flag at the top, that tells us when bounds checks are happening. And if you look, you'll see that it's flagging the same two lines as we were looking at in the disassembly. So the Go compiler itself is actually pretty good at doing this automatically. It gets better with each version as they try to avoid having to make people do the kinds of things I'm about to describe. It would normally look like this. You make a sort of a hinting access deep into the slice, and the runtime will do a bounds check on that, but then it will know that in subsequent lines of code, it has already checked that range is a valid bound, or is valid for that slice. So instead of having 4 bounds checks here, we'll have 1, and then the rest of them will eliminate. But in the case of the particular code that we're looking at here, that doesn't work at all. Because if you remember, it's this triply indirect lookup. Am I highlighting it? Yeah. It's this triply indirect lookup here, which is just like a little bit too much for the bounds check prover in the compiler to take apart. So we've got these 3 levels of indirection here. One of them's a constant table lookup, sigma. One of them's this round function thing that's a loop iteration, and then one of them's like slicing into the input data. So we're going to do 3 separate things for each of those lookups. One, we're going to take that constant table and propagate its values down into the function. Those are never going to change, so we don't actually need to be paying runtime costs to make that lookup. We can just put the constants there where they need to be. We're going to unroll that loop to get rid of that iteration. And then instead of slicing into the message buffer, we're going to allocate local variables for each of the 16 chunks of the message that we could possibly have. All of these things might or might not be optimizations in their own right, but here we're combining them specifically to convince the compiler to eliminate bounds checks. And when you do this, our code will go from looking like this to instead looking like this. You can see up here where we've fully unrolled that message assignment loop, and you can see down here where we just have like fully propagated constants into local variables. Everything is linear. There are no slices to be seen, and the compiler actually loves this. We've eliminated all of those bounds checks, and we get at the top end an 80% throughput bump. OK, so bounds checks. Bounds checks are slow. You would like to eliminate the bounds checks if you can. We haven't actually gotten rid of all of them in this function yet. There are some at the end. If you look, it's at the bottom here where we're taking all those scrambled bits and then using them to update the internal hash state. That's H. Now, the hash state is always accessed in this order, always with constant offsets, and it's always the same size. So you would think that you could eliminate bounds checks here by doing one of those preventative hints at the top. But for some reason that's completely unclear to me, you just can't. It doesn't work here. I should probably file an issue. So we can't do that. We have two techniques now for eliminating bounds checks, one of which is get rid of slices, the other of which is hint to the compiler. But we're going to need a third here. And the third is, because we have constant size, we have constant lookups, we can just replace that slice with an array. And because it's always a fixed size, we're always doing fixed size lookups, the compiler will be satisfied, and it will eliminate those final bounds checks in our compress function. As a side effect, in our finalize function, which runs during the output generation, we can also get rid of a make and copy that we were doing to copy that digest state, because arrays are copied by value and not by reference. So we don't need to do deep copies. We just get them. Anyway, this works too. Bounds checks are slow. We've eliminated some bounds checks. We would expect performance improvement here. And what we're seeing is still a pretty respectable, like 10 or so % increase, but only in that 8 bytes. But only in that 8 bytes benchmark. Why is that? Well, if you remember our benchmark, what we're doing in our timed loop is creating a new digest, writing the data, producing an output sum. In the 8 bytes benchmark, we're not writing very much. So the runtime of that benchmark is going to be dominated by new digest and sum, which contains finalize. Whereas in the larger benchmarks, we're going to spend relatively more time in write and less in new digest and sum. So we would expect, if we're optimizing something that only affects new digest or sum or one of their subcomponents, then this pattern would show up. We would get improvements in the smallest benchmark with runtime dominated by those functions, and it would be kind of negligible for the write-dominated functions, which is what we're seeing here, because that's what we did. We removed a make and a copy from finalize, which is a component of sum. And if you've optimized Go code before, you're probably familiar with the notion that allocations are expensive, and we want to minimize them. That's definitely true here too. When we go back to our pprof outlines, you can see that underneath our code, underneath G and compress, the next thing that we see is malloc. And then further down, but still prominent, there's make slice and memmove, which are runtime calls related to making slices and doing copies. So allocations and copies definitely still show up in our benchmarks here. They're just not as prominent as the math. But if we want to really get into the long tail here and eliminate some allocations, cool, we can do that. Let's literally just grep for make. This is everywhere in the code that I make a slice. And if you look, most of them are at the API boundary. They're there so that we can present an API that is idiomatic Go, that uses slices instead of fixed size arrays, because that's just nice and better, and it's what the hash interface specifies anyway. But 2 of them, here in the middle, are in our code. That decopy thing on 325 is in finalize, and that out is in sum. So let's take a look at finalize and see what that copy is about. In Finalize, we have our digest struct, which represents the hash state at any given time. And inside it is this value buff, which contains any data that we've written to the hash that has not yet reached a full block size. The hash function itself only knows how to update its state with a full block at any given time. So if we write a partial block, we have to keep it around and wait for a full block to come before we can update the state again. But in the case of Finalize, we want to go ahead and end it before we've written a full block. So we zero pad the difference between the length that we've written and the full capacity of a block buffer. Now, when I first wrote this code, I thought, OK, cool. I will make a new slice. I'll allocate a new backing array, and then I'll copy. Because when Go allocates new memory, everything has the 0 value, so I'll get an implicit zero padding effect from this. But, of course, as the profile shows, that turned out to be slow. So we got to think more about what behavior we're actually relying on here. And that behavior is actually just the zero padding. When we start Finalize, we don't really know the state of that buffer because we're reusing the backing array for each iteration. So we have the data that we've written, and we're confident in that state. But everything after the length that we've written to could be anything at all. Could be data left over from a previous hash iteration. What we want is the thing on the bottom with nicely zeroed, the difference between length and capacity nicely zeroed out. So instead of relying on implicit behavior of allocation, instead, we can explicitly zero. We can just we can explicitly zero out the rest of that. So the Go compiler knows that zeroing memory is a thing that people do a lot. And it has a capability called pattern matching, where when it sees patterns of Go code that it knows it can do more efficiently in some kind of underlying system function, it will replace that Go code with that underlying system function. And in this case, it recognizes that we are ranging over a slice and setting all of those values to 0. And it replaces that with a call to, it's either memclear or memset, but it's like one like libc type call. So instead of doing this Go loop, we can just efficiently zeroize any amount of contiguous memory. And we write it like this to hint to the compiler that it should do this. And this does turn out to be faster. But you'll see, again, this pattern of we're optimizing the Finalize function so it affects the 8 bytes benchmark much more than the kilobyte or 8 kilobyte one. And in fact, it's getting into irrelevance by the time we are hashing 8 kilobytes of data. That's one of our makes. Let's go look at the other one. In this case, it's in sum. And what we were doing previously, maybe I can show you. What we were doing previously in sum, where is sum, was this. It was not smart. Finalize was allocating, and sum was doing a full append to the input slice. But sum in the hash interface is what's called an append API. So what it actually intends for us to do is to take that input slice that it gives us and just stick something on the end of it. And a smarter way to do that, rather than an allocate and an append, is to see if the slice we've been given has sufficient capacity already to hold our output. So that's what we're doing here. We're checking the capacity of our input slice in sum, and then if we've got room, we're just going to use that. And if we don't, we'll have to do a new allocate. But often, we'll have enough room because that's kind of on the collar, and they'll give us a slice of the appropriate capacity. This pattern I think of as slice for append, because that's what it's called in the standard library a lot. So if you go read like the Go crypto implementations, they will do this kind of thing a lot, and it's more efficient than what I was doing previously. As we can see again, we get this 8 bytes, 10-ish% improvement, 1.5% in the 1K, and then literally nothing for the 8K. And if you look also at the Pvalues in the higher in the higher benchmarks, you'll notice that they're starting to get wonky. These are not statistically reliable metrics because there's not enough difference between the runs for the benchmarks to notice anything consistently. There's too much variance, or the differences are too small. So what we're really seeing here is that we're starting to get to the point of diminishing returns. We've gotten a couple of big wins, and then as we go deeper and deeper into this, we get smaller and smaller returns, even though it's for similar amounts of effort. So there are more things that you can do to this code, but they're really more of the same. They look like, hunting down every extraneous allocation, getting rid of more bounds checks, unrolling all of the loops, literally all of them, and being a lot more aggressive with breaking up functions into small inlineable things. But when you do this, you'll continue to get less and less return on your effort. So is it worth it? I have spent many hours of my life on this. Obviously, I love it. I love writing fast code. And sometimes when you need it, you just don't have a choice. But the things that I have just spoken about are really more of a library of techniques and definitely not best practices. Also, everything is extremely compiler version dependent. All of this has changed before, and it will change again. Go 1.11 changed a bunch of this stuff, like literally a couple weeks ago, if even that. So you always have to run your own micro benchmarks of this type, not only every time you make a change to your code, but also anytime you update Go, just to make sure that it still works and you're not actually doing anything that's actively bad for you with some compiler change. And then, even with all of that care and pain, you still won't be competitive with someone who has just copy and pasted a bunch of assembly code from OpenSSL. In fact, it is very hard to write competitively performant crypto code in pure Go at all. So, that's my talk. Thank you, GopherCon.